Okay, so let us start with example 3 next. In this example, you see a function given by this graph. I mean, if you want, you can write the formula for these different parts of the function, but we don't need that. Now, from this graph, we have to decide whether the function is continuous at these points and these integers, and in fact the closed interval 0, 4 is the domain of this function. So let's see. First we look at 0. At 0, let us name this A. That means in part A we are going to discuss the continuity of f at 0. At 0 we can only talk about the right hand limit. That's because the left hand side of 0 does not form a part of the domain of f. So the left limit at 0 cannot be talked about. Okay, it does not exist simply because there is no input to the left of 0. And what is the right limit at 0? The right limit at 0, of course, is 1. But that also turns out to be the value of the function at 0. So that means our function is continuous at 0. Hence, f is continuous at x equal to 0. Next comes the point 1. I mean, just by looking at the graph, you can see whether it is continuous or not. The graph should not be broken at that point and around that point. But at 1 it is broken, not from the right side but from the left side. We have the left hand limit at 1 is what? It is 0. But what about the right hand limit at 1? Sorry, here at 1 it is equal to 1. And 1 is also the value of the function at 1. Note carefully which of these points are, which of these circles are black and which ones are white. Here we have a white circle because f of 1 is not 0. Instead, f of 1 is 1. That's why we have a black circle here. So from these things, you can see that f is not continuous at 1. Why? Because the right hand limit and the left hand limit are different. So the limit, the two-sided limit, does not exist at x equal to 1. Nevertheless, the right limit at 1 is actually equal to the functional value at 1. So f is not continuous at x equal to 1, but it is right continuous at x equal to 1. F is not continuous at x equal to 1, but is right continuous there. Okay. Now the next point is 2. Because we need the graph, so let's do it here itself. C. Now, what is the limit at 2? Does the limit exist? Let us see the one-sided limits first. Let us first see the left-hand limit at 2. The left-hand limit is 1. And what about the right-hand limit? The right-hand limit also turns out to be 1. If we come from that side towards 2, then also the limit is 1. And that's why in this case the limit exists. Thus, that means the two-sided limit at 2 exists and it is equal to 1. But in spite of that, the function is not continuous. And the reason, of course, is that this limit value is not equal to the value of the function at 2, which is 2. And in fact, you can see that this is the case because the the value of the function at that point lies above the limit. So here the graph is broken. F of 2 is 2. So f is not continuous at x equal to 2, and in this case f is also neither left continuous nor right continuous because none of the one-sided limits is equal to the functional value. Next comes the point 3. At 3 the function will be continuous, and you can see that in spite of having this sharp turn, the graph is nevertheless at 3 and around 3 it is in one piece. More rigorously, we have the left hand limit at 3 is what? 2. The right hand limit is also 2. And that is also equal to the value of the function at 3. So f is continuous at x equal to 3. And finally, we look at the point 4. At the point 4, because 4 is a right boundary point, we can only talk about the left hand limit, not the right hand limit. So what is the left hand limit? The left hand limit at 4 is 1, but that is not equal to the value of the function at 4, which actually is 0.5, 1 over 2. So f is not continuous at 4. So that's the thing. So among all these points, the function is continuous at 1, not at 1, I was looking at this, at 0 and at 3. At the other points it's not continuous. At 1 it is right continuous but not continuous. At 2 it is not continuous, it is also not any one-sided continuity is also not there. At 3 it is continuous, at 4 it is not continuous, and of course there is no one-sided continuity. Now if one applies the results about limits of functions, especially algebra of limits, to the case of continuity, one gets rules of continuity. And these rules are given in the form of a theorem. This is theorem 6. Continuity of algebraic combinations of functions. Algebraic combinations, and the statement is pretty simple. If f and g are functions continuous at x equal to c, then the following functions are also continuous at that same point. And using these rules of continuity, we will be able to decide pretty easily about continuity or discontinuity of some complicated functions, which if you use the definition, the limit definition for continuity to those functions, then you may get confused because they are fairly complicated. So the sum of two functions which are continuous at C is also continuous at C, and so is their difference. Number 2, their product is also continuous at C. Number 3, k times the function f is also continuous at C, where k is any number. Number means it's any real number, it's a constant. Then number 4. Number 4 is the quotient of these two functions f and g. f over g is continuous at C. Well, okay, we need not have written that, but anyway, provided there is a condition, of course, because we are dealing with division, provided g of C is not equal to 0. And then there is one more. This power where the exponent is a rational number, m and n are integers, is continuous at C. Here also there is a condition. Provided this power is defined, it makes sense in an interval containing the point C. It has to make sense at C, and not just that, in a small interval it has to make sense. From that interval, if you take any x, then this should be a real number. You can of course guess why we need this condition, because sometimes you may have problem. For example, if your fx value is a negative real number and you have m equal to 1 and n equal to 2, then that is not a real number. So to get rid of that problem, we need this condition. Using these rules, we can break down complicated functions into simple functions, and their continuity will give us the continuity of the complicated function. And besides this means from these rules, we also get something else, continuity of polynomial functions and rational functions. That is the next theorem. And rational functions. We already know what polynomial means, and rational functions are quotients of polynomials. And the statement is simply this: any polynomial is continuous at every real number and any rational function is also continuous at every real number except at those where the denominator is 0. In fact, at those points the rational function is not defined at all. And you can of course understand how it is that we are getting theorem 7 from theorem 6. I will still say, I will give an example of how that happens, but let me first put some ink in this. Denominator is 0. So as an example, let me just show you this. Suppose you have this function. I think the author has given an example. Yeah, so we can see this example itself. Example 4. So we first consider two polynomials, and the polynomials the authors have considered are these. One is this degree 4 polynomial, and the other one is this quadratic polynomial. Five x times x minus 2 are both continuous at every real number, because they are polynomials by theorem 7, that is the thing. And the function hx, which is the quotient of f and g, is continuous at every real number except at x equal to 0 and x equal to 2, because at those 2 points the denominator is 0. Now before we just leave this example, let us actually see how we can use theorem 6 to conclude that, say, this particular polynomial function is continuous, and from that we will understand how any polynomial function is continuous everywhere. We already know that this function is continuous. Say, let me call this alpha x equal to x. We have already seen this many times. This is known as the identity function on the set of real numbers. This function is continuous. So by applying the second rule for continuity, alpha square is also continuous, because in place of f and g you take alpha itself. So you take 2 copies of alpha, you multiply them, you get alpha square. Alpha square will be continuous, and alpha square is nothing but x square. and you keep doing this. Then with alpha squared you take another alpha, you multiply those two things, that will also be continuous. So this way eventually you will get this. This function is also continuous. Similarly, if you consider this constant function beta, that is also known to be continuous. Any constant function is continuous no matter what the constant is. And then you use part 1, that is the first rule of continuity. You then get this thing. This function should then also be continuous, which is nothing but our f. In a similar manner, using the other parts of the rules of continuity, you can conclude that gx is also continuous. And you can understand that just like this, any polynomial function is going to be continuous at every real number. And this is a consequence of the fact that the identity function is continuous at every real number, and any constant function is also continuous at every real number. And when you take quotients of such things, then they will also be continuous at every real number except at those points where the denominator becomes 0. At those points the function itself is not defined. So that's how this theorem 7 comes. Now let us see another example. Here we have not a polynomial function but a different function, it's the absolute value function. So consider the absolute value function. You already know what this is. It is equal to x if x is non-negative and minus x if x is negative. Now if one draws the graph of this function, the graph has one sharp corner at x equal to 0 and it's just a straight line everywhere else. Let me just draw it somewhat carefully. So this is the graph of your absolute value function. So from the graph itself you can see that it is continuous at every real number. Next comes the trigonometric functions, the collection of all trigonometric functions. These are much more complicated than polynomials or rational functions. These are neither polynomial nor rational functions. So this is example. Has it been given as an example? Yes. Continuity of trigonometric functions. So we don't know it yet, but in chapter 2 we will show that these two functions are continuous. The sine and cosine function are continuous at every real number. Okay, this we are yet to see, but we will see. Hence, the quotients of these functions, which we know as the other trigonometric functions, that is tan x, which is sin x over cos x, then cot x, which is cos x over sin x, secant x, which is the reciprocal of cos x, and cosecant x. Yeah, instead of writing cosec, sometimes we also write, make it even shorter and write CS, but I like to write cosec. Are also continuous everywhere where they are defined, that is where the denominators are not 0. And in fact, from what we already know about these functions, we know precisely what those real numbers are where these denominators are 0. Cos x becomes 0 precisely when x is an odd multiple of pi over 2, and sin x becomes 0 precisely when x is a multiple of pi. So in these functions where you are having cos x in the denominator, you have to avoid the odd multiples of pi over 2, except those points. Everywhere else, tan x and secant x are continuous. Similarly, except at the integer multiples of pi, cot x and cosecant x are continuous everywhere else. Where they are defined, that is where they have values. After this we will see continuity of composition of functions and some other things which we will do in the next video. So that's just it for tonight. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.